alive. Oh, it's alive. It's alive. It's alive. It's alive.
It's alive. No, I don't do it as well as he does, but it is alive. A new science project is trying to recreate that Frankenstein spark by creating a new form of life from scratch. Dr. Gerald Joyce, a professor at the Scripps Research Institute, is one of those scientists pushing the boundaries by trying to synthesize life using a thimble of liquid. Well, you have our attention now, Doctor. How do we, or you, I should say, create new life?
Hi, Randy. Well, you know, what we don't do is go borrowing parts from the mortuary. So the game here is not to make life from existing life, to not to try to make another biology using parts from our biology, but to try to make a biology from scratch. And that means from chemistry. Because, of course, when our life form began on this planet, it came out of chemistry. And so that's the goal of researchers in the laboratory, is to, starting with chemicals, non-biological components, build something that we would consider to be alive.
Mm-hmm. So it starts with what? They have to self-reproduce? Is that where it begins?
Yeah, so what is life all about? I mean, a key part of it is, of course, self-reproduction. So the parents need to make progeny and so on and so on. And we have that now. We now have molecules that can self-reproduce, that can indefinitely produce copies of themselves, and those copies produce copies and so on. But it's not just reproducing. It's also carrying genetic information, transferring genetic information down the generations. And that's also what's new in the laboratory. It's now possible for these self-reproducing molecules to transmit genetic information to their progeny.
And what can a second form of life mean for us? Why is this important? Why should we care about this?
Well, you know, right now it's pretty low bit content, and I wouldn't call what we or others have done yet truly alive, because it really is not evolving much yet. But the key is to understand how life works. It works through Darwinian evolution, and to have a system, a chemical system in the laboratory that also undergoes Darwinian evolution. And that's what can happen now. So then you say, what will it evolve next? And that's what's going on in the laboratory, to try to give the system more capability to evolve more complex functions, including some things that might have applications.
So how can it help us in the future?
Well, so, you know, here we have little molecules, and they're not much to look at, but I can give you a sense here, little test tubes of molecules, and as I say, they're not much to see, but we track them with little fluorescent probes, and if you can see it on the left, the sort of the before, and on the right, the after. But the afters keep, you know, breeding and making more and more copies. So what you have is kind of an amplification engine, something that can just make more and more copies. Now, if that engine is triggered by some event in the environment, say the presence of a chemical or a drug or a metabolite, then you have a sensor for that chemical. And so that's the application of this.
It's fascinating, Doctor.
But I got to say...
we can't have you say it anymore. We're out of time. But, Doctor, we appreciate it, and best of luck with it. Thank you.
Very good.